Hello, friends. Neotoy Store here yet again. I hope you're ready for another one of my long, rambly videos that I'm so famous for. So, this right here is a continuation of a project that I started a long time ago, many years ago, and I don't know. For me personally, it's kind of an interesting thing to see, like how far I've come as a modeler and someone who understands 3D printing. Some of you may actually recognize this design even though it's changed quite a bit from its original form. Uh, the original is probably most similar to this design right here, which has a few little issues as you can see. However, um, when I designed this was back in the days when I was using Shapeways to do all my 3D prints. Just FYI, this video is not so much about this model as it is about 3D printing and some of its idiosyncrasies, and one particular topic that I wanted to focus on in specifically, which is build plates and adhesion on the build plate for FDM 3D printing. But yeah, the thing I wanted to say about this is that originally I made the design and I sent it to Shapeways, and they 3D printed it out of PLA. And this was many years ago, but even back then, they had this ability to use different materials for support. So they could use a type of support material that would dissolve in a solvent. And so, in other words, you could print what you wanted in the durable PLA and then print the support in a dissolving material. And that would allow you to do crazy things like, it's hard to see, but there's little channels in here that go through these walls. And when I first designed this, I didn't understand anything about 3D printing, and so I made those supports or those channels just square. And because of that, if I were to print this myself with square channels, the filament would just pile up inside there because of gravity, and it would be trying to deposit material on top of thin air. And that's something you just can't do in 3D printing without support material, which I'm trying to avoid for a variety of reasons. But mainly, if I had to pick one reason that I don't like to use support material at all, it's because I think it's wasteful and just kind of inelegant in general and shouldn't be necessary. Which really kind of brings me to the broader topic of this video, which is sort of the state of the art of 3D printing in its current form, especially FDM, because I don't think this really applies as much to resin-based 3D printing, which, uses a very different principle, although similar enough, but it doesn't suffer from a lot of the same problems. It has its own problems, but not the one that I specifically wanted to talk about, which is build plate adhesion. And now, for those of you who don't know, who may not be obsessed with 3D printing, build plate adhesion is basically like this. So, actually, I think I'll use this model. This was an aborted print because I started to notice on the little camera that it was warping and pulling off of the build plate. So normally, when you're printing something, the build plate, imagine this white plate here is the build plate, and the tooling had the extruder, the little hot thing that squirts out the plastic and lays it down on the build plate, is pressed up against that plate, right? And it starts to squirt out the plastic, and the plastic's in like not a molten form exactly, it's like a semi-liquid, semi-solid state. And and it starts to sort of like ooze and squish out onto the build plate. And if it doesn't stick to the build plate, immediately you get problems because the tooling head is moving often at a high speed. And if it keeps moving and the filament, the liquid filament, is not sticking to the plate, it will just get pulled along, and then your layer's ruined. And basically from that point onward, you're just going to get what we call spaghetti, which is just a big pile of extruded filament that doesn't form a shape and isn't coherent in any way. And now that's just the first challenge, right? If you can get past that, then you have the next problem, which is thermal warping due to expansion and contraction. I did a lot of research on this because this is a very common problem and something that just utterly plagues 3D printing. For example, what happens is when the filament comes out, it's hot, and that means that it's expanding. And then as the print continues and the layers rise, the lower layers start to cool, and then they start to contract. And then what can happen is that the contraction causes the lowest layers to actually lift away and start pulling off of the build plate. And you can see this very clearly here on these corners. What happened is, I mean, that's a really pretty dramatic distortion. It's pretty bad too on this version. You can see where it just started coming right off of there. Look at that massive distortion there. And then of course, what that does is it completely offsets the layering, right? Because now a layer that was supposed to be a millimeter below is being pushed up by the warping, and then the extruder's trying to lay down filament on top of, an area that no longer exists and that it's much higher. And so you get all of this other distortion on the top layers. So it pretty much destroys the print. Now, there are many, many solutions online that you will find to this problem. You can wade through forums, and I'd like to at least give the 3D printer manufacturers a little bit of credit. And nowadays, when you buy a modern 3D printer, what you'll have like a suite of techniques that are designed to try to mitigate this problem. You'll have heated build plates, right? That keeps the bottom layers of the filament warm, so there's less thermal expansion and contraction variance. You have enclosures, right? So you've got walls around the 3D printer, sometimes insulated, so that it keeps it hot in there at a consistent temperature and environment. And that can also reduce that phenomenon. And then you have auto leveling, so like the build plate can auto level, so you get the first layers are nice and consistent. That's also useful. And then you have textured build plates, PEI, that has like a surface that is has lots of topology complexity. So when the filament is squirting down on there, it goes into these little crevices and it sticks, right? So that's one way. And then all of these methods, there are many more, even like cleaning your build plate with alcohol every single time you use it. All these methods are designed to mitigate this one problem, which for me personally, if I have to identify if there's one thing with FDM 3D printing that still needs to be worked on, and a lot of effort and energy and R&D needs to go into solving this problem, it's build plate adhesion. Because here's the issue for me, is in any kind of modern manufacturing or robotics or high precision is involved, the tolerance for errors like this would be very low, and they are very low in a more industrial setting. But when it comes to consumer grade 3D printing, I just have to say, like, the margin of error is way too high in this particular area. The fact of the matter is, like, it's a huge amount of waste that is generated by failed prints because of this one factor. So I just want to, like, say, if you're a developer of 3D printers or a manufacturer, please devote a significant amount of R&D and attention to this problem, because it is solvable, and it is a problem that can be cracked if enough time and resources is put into this. Because I have waded through many forums and I've seen all kinds of hacks that people have done to kind of solve this problem, and there are solutions. For example, I came across the forum post the other day. I have not tried this, but apparently you can solve this problem specifically by taking 200 grit sandpaper and wiping it in one direction across a PEI plate, creating extra, pores or grooves in the surface that the material can cling to. So there's an example of, like, how if you were applying science to the design of build plates, you could, experiment and iterate with something like that, because it's about tolerances, right? It's about materials, it's about precision tolerances. We just need to nail down exactly the texture and the topology of that build plate that results in optimal or almost perfect adhesion. Yeah, I forgot to mention, people do shit like spray hairspray on their build plate, put glue on their build plate, put painter's tape on their build plate. All of these ridiculous hacks, I'm telling you, it's degrading as engineers, as inventors, as people who work with these precision, high-end, super science level tools. This level of hackery should not have to exist. And as I said, it's within the capabilities of the designers and the engineers to figure out how to engineer away the problem of bed adhesion. And we shouldn't have to be doing these hokey witch-like spells, run around your 3D printer 3 times and say a little prayer before you hit that print button so that you'll get good bed adhesion. Okay, my vision, once the build plate has been engineered properly so that it doesn't require this level of sorcery, you would not need to put alcohol in your build plate between printings. Like, if the build plate is dirty, that's one thing, but just between printings, you shouldn't have to clean your build plate if it's just being touched with, like, PLA or a filament or whatever. So that's something you shouldn't have to do. Auto leveling, obviously, that's just a good idea no matter what. So I feel like, and that's a technology that's already been added. Heated build plates, that makes sense. And enclosures also makes perfect sense. These are parameters that I think are common sense parameters that should be built into every 3D printer. So I would exclude those for modification, but really what it comes down to is the surface and the technology that goes into that surface of the build plate, because clearly that's just about getting those perfect tolerances of the right topology to create just the amount of attachment for the print that it's not gonna pull away. And clearly most of the build plates are engineered fairly well. However, they haven't hit that sweet spot yet, and so that's my appeal to manufacturers. And I just want to say, like, I solved this warping problem without doing any of that shit, aside from using alcohol on my build plate, which I did do, and I do just because, as I said, it kind of makes sense. I do have an enclosure that I created myself, but I was using alcohol every time. I was um, printing with my enclosure, and I was still getting these horrible warps, right? I tried multiple materials. That was not the problem. Uh, Thermal variations, not the problem. Um, there's not enough information or science about these problems for us to properly solve them. That's another issue. So I feel like there needs to be a lot of research done in what makes things fail. And personally, I concluded, I was like, okay, I've narrowed down the variables. It's not all the common suspects, it's structural, right? Because this is something most people don't think about when they're 3D printing, but everything you 3D print is like a physical heat sink, right? The way it disperses heat affects the way the layers cool. An object like this, for example, it's basically a type of heat sink with the heat expanding or conducting through the vein-like surfaces and being dissipated around the edges. So that's gonna, focus. Like if you were to look at this with a thermal imaging camera, you would see where the focal points of concentrations of thermal energy and where the deficits were. And that's the real reason why this was warping, not for any of those other factors. I have a heated build plate, I have an enclosure, etc. Like I have good adhesion, but you can only do so much with the physics that are available. So the first, attempt, I was like, okay, a lot of people are having trouble with sharp corners, right? That's like clickbait for poor bed adhesion. So I rounded all the corners, and guess what? Didn't make a damn difference. This is a perfect example how there's like all this misinformation out there about how these things work and why the phenomena emerges. So anyway, I like the aesthetics better, but it didn't solve the problem. So at the end I was like, okay, I have to solve this in an engineering way because my designs are not designed to be printed under ideal circumstances. I want anybody with any piece of shit printer to at least be able to get a decent print if they're determined enough. And so I came to the conclusion that if I just created some stability and provided a different thermal avenue for the heat to dissipate along, that might reduce or eliminate the warping. And it did. Everything was the same. The only thing I changed to the design or any of the variables at all was to add these little stabilizing fins onto the edges, and now I have zero warp. And the reason I was able to figure that out is because along this edge there's zero warp. It's only when it gets to the corners that it warps out. So it's these little clues that help. Real applied science would have been able to solve this problem way better than just a jackass like me in his home laboratory. But I did figure out how to solve it, and now I have a model that prints reliably without waste and without any witchcraft. It just works. So yeah, this is a bee feeder. And I have a video on my channel of the original that I made years and years ago, which I'll probably link in the description, so if you want to watch it, you can. Yes, a lot of hobbyist fields, they end up degenerating into this sort of pseudo-scientific witchcrafty thing where people do these rituals. It's a human nature thing. You can't really blame us for that. It's just programmed into our DNA or whatever. But science, contradicts that. It goes in the opposite direction. It's all about empirical data, reducing variables, distilling information, keeping really good records, and not doing things superstitiously. We need less of that in 3D printing. We need the engineers and the scientists to help